Okay, in this section, we're going to look at the idea of the normal curve, kind of what it is and where it comes from. And you'll notice 17.1 doesn't have any homework problems because it's just an introduction to the idea of this. But the idea is also really important because when you get into 17.2 and 3 and you're working with the numbers, it's good to always go back to what does this actually represent? Because when you're looking at the numbers, they do start to feel maybe the percentages a little bit random, but you'll see that the normal curve is actually a naturally occurring phenomenon in real life. So here they have a table where they show different heights of NBA players and how often those heights show up. And so we notice that it looks like 25, 30, 36, 42, maybe 6, 7, 6, 8, 6, 9 are the most commonly listed heights. And so if we put a bar graph of those, of this frequency table, it would look something like this. Okay, so for example on here, they show the normal curve, this red one, and then they show the curve that would kind of fit our data. And so notice it's a little more skewed to the right, and so that's probably not a coincidence. And the red curve represents if you just take the general population and you map heights. A normal curve should pile up around the mean. So why is this one skewed more to the right? Well, it's probably not a random coincidence. It's that there's taller players in the NBA than there is in the normal population. And so it makes sense that it's off center a little bit. It doesn't fit the normal curve perfectly. And so same thing that we were just saying, that if there's a lot more taller players in the NBA than there are tall people in the general population. And so it's skewed a little more to the right. And here's one showing SAT scores. So lowest you can get is 200, highest you can get is 800. And so here they showed the frequency. And now notice this will probably fit more normal because it's a really big sample size. We have like hundreds of thousands of scores for a total sample population here of almost 1.5 million. And so notice this, a little more like we expect, almost lines up perfectly to the theoretical normal curve. Is that most people, if the mean is here, most frequent would be around the mean or scores near the mean, and then less frequently people do really poorly or do really, really well, but they mainly pile up around the mean. And so that's what the normal curve is, that you know that data in real life, if something's the mean, then most often a lot of data is going to follow that same trend. Like say on a test, most people would get around 70, a few might get 100, and a few might get, 0 or almost 0. So in general, normal populations pile up around the mean. And so this one, you notice it's really close. So the closer your data is to the theoretical normal curve, then the better you'll be able to use the normal curve to measure. And so approximately normal means it's not perfect, but they fit pretty well. And so the better it fits, the more you can use it as a measuring stick for whatever data you're actually trying to find something out about. And so the normal curve would be if it was ideally perfectly symmetrical. So if we had tons of data points, and then what they're doing is finding the percentiles on that normal curve. So if you're right in the middle, you did better than 50% of people and worse than 50% of people. They figured out all the percentages for you, and so then you can use that normal curve as a measuring stick for whatever your data is if you know that it's approximately normal. And so the closer it fits to the perfect theoretical curve, the one that's perfectly symmetrical, the one that we'll use to measure all the other ones against, then the better you can do with using it to measure your real life data. And so N, like always, is the sample size. Now, in general, the bigger your sample size, so we saw like in the SAT one, there was 1.5 million test takers. There's less room for outliers when you have a bigger data set. So let's say if you take 10 SAT scores, maybe you got 10 people who all did really well. And so there's a chance that can happen. If you take 1.5 million scores, it's probably going to fit the average a lot better. You won't have 1.5 million just by coincidence people that you interviewed who all did really well or really poorly on it. And here's one with test scores. I think we did this one before with the 75. Yeah, this same data set. So 75 stats tests. And if we look at this, it's approximately normal. I'd say this part maybe is a little bit higher, and we have these two kind of outliers, but in general it piles up around the mean. And so also we could do this as percentages, so instead of saying the count, we could say, oh, about, let's say this one, about 12% got a 12 on this. If you want to know how many students that is, you could say, well, what's 12% of 75? So same thing we were saying here. You can, if you have n, the total sample size, and you have percentages, you can figure out how many students any one of those was. The really interesting thing about this, though, is that you can see it in real life. So let me really quick show you a little example here. So they take these balls, and notice up here at the top, there's probably more of them than you can see. Kind of reminds you of, blanking on the game show. The Price is Right has the Plinko game where you drop the little coins down and they represent money. So picture every time a ball hits one of these little pegs, it could go left or it could go right. It's got a 50-50 chance, right? This is nice and evenly distributed and level. And then the next time it hits one, it has a 50-50 chance. And so watch what happens if they put a whole bunch of balls through here. Every single time you do it, it might not pile up exactly the same, but the more balls you have, it'll get closer and closer and closer to this perfectly symmetrical theoretical normal curve. So notice one time it looks like that. Another time looks a little bit different. But in general, if we could do this with millions and millions of balls, they would get closer and closer to being perfectly on that curve. Because yeah, like, if I'm looking at it back here, we'll stop it when one fills up. What are the odds that a ball goes right every single time in a row? Well, pretty low, and so it's not surprising that down here you see very few balls that went right or left so many times in a row that you ended up with some over here. And so some of these ones, they could go left, left, right, right. They could go left, right, left, right. You have more of them in the middle just by chance. And so when we're looking at the normal curve, it really does come from a real life kind of model of what would happen. I think there's another one of these that looks kind of cool. It's like in a museum. And it's got a big conveyor belt over here dropping the balls in. And so the more they do, then the more accurate normal curve you get. So all the balls are falling through really quickly. We'll get to where we can see it start to fill up. And so notice, yeah, you can get outlier ones that go a lot right and a lot left. But as it goes down, it starts to better and better fit the actual normal curve. See if they give us a nice zoomed out view of this or not. Yeah, and there's one really outlier. It's only one, there, another one just fell in. Only two balls went left, 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 left enough times to end up in that area. And so notice if you have enough of them, it ends up fitting the normal curve pretty well. And so the more bigger sample size you had, which in this case would be more balls, the more perfectly it will fit this curve. But it is a naturally occurring kind of phenomenon. It's not made up. They know that given a random scenario, it will end up like this with a bigger and bigger sample size enough times. There's a really big outlier. One went way over to the right. It'll end up like this enough times that we can use this shape to measure data because we know a big sample size would end up this way anyways. Also, these things where they drop through are called a Galton board. So if you Google it, there's a whole bunch more videos out there. They're kind of fun to watch. So the biggest idea is when you're in 17.2, 17.3, and the numbers feel random, this is a naturally occurring probability distribution. And so we can use this to measure our own data without having to recreate this experiment every time. So someone else has already taken all the measurements on this curve. We're just going to use the measurements. So this curve is like our measuring device or our ruler for our own data.